Good. So let me share the screen. So the people on Zoom, do you see me? And do you hear me well?
Yeah.
Great. Okay. So let's. Good. So let me just also make this one a little bit. I think it is. So can you read the page? So it might be a little bit. I mean, my handwriting. Unfortunately, that's it. I cannot change it. These things, but I try to write this one clearly and give more examples. And again, if you want to, don't read my handwriting. Please read the typed ones. So we have the LaTeX on the website. These are the PDFs. You can just not my handwritten notes, the actual type notes. Good. So we talk about induction and algorithm. That we had, I mean, some algorithm. For example, the last one was like a simple algorithm that gets a number and make it binary, that number. And so that's how you can prove that it works. And the idea is that generally we need to find a while loop or important while loop and have some induction such that we can prove that it works. Good. Now, let's see. I mean, another problem actually that now this is actually a typical thing. I have been involved in some of these interviews on either side, and I of course heard from my students and others. So the problem that generally, as I mentioned, this class would be very useful. I mean, of course, like these are the important things that if you want to continue for graduate studies or industry, that would be very basic. And we are talking about basic proof, and that basic understanding will help you a lot. But also in the interviews, one of the things that they are doing a lot, and I think this book, as I mentioned, it's great about it, this introduction to algorithm creative approach, is seeing the problem from another view. Because if you see if somebody tells you the problem, you see, oh, it's easy, let me just do the code. And in the interview, that's exactly the wrong thing, that you should not do that. Because generally, that way that you want to do it probably is not an efficient way. It may take a lot of time. And you need to actually maybe think for 5 minutes. And I think they generally also say that you should talk also with the person who is interviewing. If this is, there are some of them, you need to solve some particular problem. Some of them you are solving with the person who is there. He gives the problem. You need to ask problems, and they want to check that you are actually communicating well. But generally, the idea is that the first solution that comes to your mind is not the correct solution. So, and here again, induction plays an important role here, but also this next view, or the view from the other side, it can be very helpful. So let's see this problem, and that's actually very good. And we are seeing actually a few of them this in this session and probably next session. So what is this and again, I have mentioned previous time, please read in the book, the chapter 2.13. These are the common errors in induction that you should avoid it. Good. Now, so this is, let's see the one-to-one matching. Let f be a function that maps a finite set A. So it's essentially the map the function into itself. So essentially, you can think about this. This is A. And again, I mean, this is actually interesting if you work, for example, with STL in C++ or dictionaries essentially in Python. These are like the one that giving this mapping to you. Good. So that's the input that is given to you. So it is from A to, so you say A, it is the numbers 1. So it is 1, 2, and this is 1, 2, 1. So these are this is the mapping. So mapping is that from each of them, one, it goes to, there is one key essentially, go to one number. So this is another example that they have it. This is the mapping that you have it. So, and it maps because there is a key essentially for each of them. So the key should be unique. So it means that from one goes to one, from two goes to another one, and so on. And maps it from A to A. So the domain actually is equal to the initial set. Now, what is the goal? The goal is that you will call this f one-to-one function if this is somehow mapping from both sides, in a sense that not only we have it here from the, I think from the left-hand side, you go one element, the degree of each guy is one. It is one-to-one if the degree on the other side is also one. So it should be no case like 2 and 3, both of them goes to 1. This is called one-to-one function. Essentially, I will say is a matching actually, such that each guy has a degree, one here and one here. They have out degree, this guy they have in degree. Is the problem clear? No, what is the goal? The goal is that, I mean, this function is given to you. This is not one-to-one. It is just a mapping. You want to find the largest largest one-to-one mapping of f. So what's the meaning of that? It means that, I mean, like, for example, here it is one-to-one. Maybe here, I mean, you cannot have what's 1 and 2. You may want to take only this guy and this guy. So if that's the only thing, then the size of this would be 2. But maybe you can make it 3. If the whole A is one-to-one, in that case, the size should be what? N. By the way, the people on Zoom, please feel free to unmute and answer as well. Good. Is the problem clear to everyone? Okay. So this is the problem that is given to you, and this is the input I'm giving to you. You need to write the program. That's essentially you have 45 minutes. I mean, this is like the style of interview I'm talking about. But here now we want to discuss it. And again, so what is the form generally they are giving it? What would be the input to this problem, for example, that you need to read it? Yeah. Go ahead first. Like a map structure. You know, but I mean, generally when they give the input to you, you need to read it from the essentially scene, like from the essentially a text file or from the input. So then what should be the input? Yeah.
So first they give you the number n, yes, in a line, and then they give you an array length n or less. That gives you the mapping of.
Yeah, it is not an array. It is, you can say, it's a text file that in each line it just write what it. So first we say n, then because we know that it is mapped from A to A, so then from 1 to n they are giving. They don't need to say 1. They say 1. They just say f of 1, f of 2, f of 3 to f of f. That's the input. That's the one that you are doing it. You can of course read this one and make a mapping in like a C++, or you can do it using dictionary in Python. Dictionaries are the same as that. So that's the input. But how do you want to find these guys? Yeah.
So start with the full set S.
Yeah.
And the full set A, actually.
First one question. Have you seen this problem before? Yes. Okay, so don't mention the answer yet. Have you seen it before? Okay, so then go ahead.
I was thinking we should so we could establish the smartest mapping.
Yes. Okay. So let's see. I mean, because here I want to actually we will discuss the actual solution. But here I want to just make sure that you will actually get some ideas about exponential time algorithms and other efficient versus inefficient algorithms. So what is the difficulty of this problem? The difficulty is this one. So consider, for example, here, this element 1 here. Good. So there are two elements that have been mapped to this element, 2 and 3. The question is that, I mean, like, you know that in the final things, there should be, the degree of 1 should be 1. Good. If the degree of 1 should be 1, it means that one of the 2 and 3 should be not in the matching, in this 1-to-1. But this is the question. As long as you have, as soon as you will come to this question that, of course, the degree can be more than 2. It might be 3, 4, or more than that. But one of these guys at the end would be the solution. You don't know whether that guy should be 2, 3, or anything else. For example, if you consider this case again, let me just draw it with a different thing. You see here, actually, you might be lucky here. Because why you can be lucky? Because here, if you choose 2 and 3 here, if you choose between 2 and 3, if you choose 3, then 3 goes to 1 and 1 goes to 3. So this is at least 1-1 matching. It may not be the maximum one. We want to get the maximum size. But I mean, but it might be the case in some cases that you have, I mean, you have the option essentially that you will select, 2 instead, and that is the best. Or it might be actually the degree of these guys might be more than that. You know that only one of them should be there. As long as there is such a problem that happens, it means that you have a choices. Then what type of, results can we get it out of it? Then you have these choices. And of course, these choices can happen for 1. It can be for other numbers. Maybe actually say that all the degrees of the other side in this side, all the degrees are essentially 2, correct? So there are half of these guys which are 2, and the other half are 0. This is n/2, and this is n/2. So essentially, it means that every guy here, it goes to, all guys are just going to here. And no one is going there. So here we have n/2 elements. Each of them, we need to decide which one should be the correct answer. We need to choose one of them. Maybe at most, actually, maybe none of them, but at most 2 of them. This is the option. So for example, for this guy, we can say that, this guy should be in the set, or this guy should be in the set, or maybe none of them in the finals. So in some sense, we have 3 choices here. And we have n/2 guys. This is very important, these multiplication rules. That if, this is actually the people may make a mistake, and that's very important. So if you have 3 options for the first guy, 3 options for the second guy, 3 options for the third guy, and so on and so forth to n guys, then how many options you have total?
3 to the n.
What's that?
3 to the n.
3 to the n. And sometimes, the people make a mistake and say 3 times n. That is wrong, very wrong. It is actually 3 to the n. And you can, make sure that if it is 3 to the n, then this problem, then you don't get it. If n, I don't know, becomes, 30, 40, probably there is no chance that you can even solve it. Even your grandchildren may not see the result of the program, unless you want to do some optimization. So, and one other interesting thing, so this set of problems that are given to you, generally they are also giving you, this is actually one question if it is not given to you. Say, what is the range of n? It might, if somebody say, oh, the range of this problem is n is at most 20, then you may think maybe that's the right answer for this, because maybe 2 to the 3 to the 3 to the 20 is not a very big number. Or maybe if it is, you can do some, this is that kind of backtracking, or branch and bound it is called, or exhaustive search. So this kind of, exhaustive search that you are doing, you will try all possibilities, And maybe you can do some kind of branch and bound everything. You can make it small. But if n is given to you, I don't know, 1 million, you should immediately know that this solution does not work. So from the range of n, I mean, you should know that even I will say 100, you should essentially, this does not work. So in some sense, like if there is some person in the interview, the first question, if that is not given, say, what is the range of n? That gives you the hint what type of algorithm that you need to. And we are discussing different algorithms. Generally, there are these three types of algorithms. These are some kind of a large set of algorithms. This is called greedy algorithm, that you will make a choice and you don't change your choice. There are some algorithm which is dynamic program. There are some algorithms like exhaustive search, it is backtracking algorithm or branch and bound algorithms. There you are doing exhaustive search. Maybe you will cut some of these searches and you are doing more smartly on them, but that's the general way that you do. There is another one. It is called dynamic programming. So dynamic programming somehow is similar to backtracking algorithms, and somehow is similar to actually the greedy algorithm. The idea is that when you try to do this exhaustive search, you can actually encode all possible solutions in some small space. It is also called sometimes memoiz algorithms, like that. This algorithm, whenever you compute one of them, then you will write it in this array or in this space that you have, such that the next time that you will come, you don't need to compute it again. It turns out, actually, if there is such a nice array that you can save everything there, the running time would be actually polynomial. Why? Because each time you will write it down. So in some sense, you don't, each cell of the array, you will write it at most 1. So if the array size n to the 2 is small, by small I mean it's not exponential, it's polynomial. If it is polynomial, then it means what? It means that the running time would be polynomial. So this is actually, we will talk more about it, but this is the general idea that you need to have it. That you have greedy algorithm that you will make a choice, you will make a smart choice and you don't change it. There are some algorithms like exhaustive search, you will try all possibilities. Some are in between, that you can actually all the search things, it can be somehow memoized in some like a small array, such that you will save it, and each place in the array you will write it down at most 1. It means that in total, actually, generally the size of the array would be your running time or some polynomial on that one, so you have a good algorithm. Dynamic programming can be very complicated. Greedy algorithm also can be, I mean, very smart and say like non-trivial problems. But dynamic programming can be more complicated. If you go, I mean, to maybe more advanced set of problems, then in those cases, actually, they may give you some dynamic programming to solve. Otherwise, generally, either you need to do backtracking, or actually lots of the times are greedy algorithms. But these greedy algorithms also can be very tricky, because if you don't see the right answer, you may do backtracking, or you may do what? Like not the correct way, or not the correct running time. Good. Now, here, as we have seen it, so this is the issue that with this, so I wanted to give some ideas about what do we do essentially with algorithms. So here, as I mentioned, for this one guy, if you have these choices, or the case that we have it, so it is 3 options here, 3 options here, 3 options here, would be 3 to the n, and 3 to the n would be 2. So it means that this is not the correct way of handling the problem, especially if n is small. Good. Okay, so let's think another way. So see this. So one other way that you can think about this algorithm is that you may try all possible subsets of these guys. So you know that the solution should be a subset of these numbers. Good. You will try all possible subsets of this and say whether on this subset, this function is a 1-to-1 or not. What's the meaning of 1-to-1 on a particular subset? It means that if you consider this subset, there should be nothing goes out, no such things. And everything so should come to itself. And the degree of this guy should be, there should be nothing like this as well. So if you consider any subset of S, this is a subset of S. So for any subset of S, you can try this one. So if a subset is given to you, what would be the running time? This is, we are talking with the own notation. To check that whether this is a one-to-one mapping. Yes?
Big of n.
Why big of n?
The size of the domain, the number of elements.
Okay, so but you should see what are the operations. So again, somebody asks you write the code for that. I mean, we are not writing the code, but you, I mean, actually, some of them they may not, you may not write the code, but you need to explain what you are doing for that. So is the problem clear? The people on the Sky on Zoom, if you have a question, please ask as well. Please unmute. Yeah.
Yeah. So the mapping that we're working on from A to so like that mapping doesn't have to be one to one. So if you were saying like one can have two, if we do with two.
Yeah.
The mapping doesn't have to be one to one for the entire set.
Yes, for entire set is not one-to-one necessary. If it is the case, then, but for a subset, it might be one-to-one. And then we want to find a subset that has the maximum size. The question is that somebody is given to you, this is a procedure that somebody asked you to write. Say, okay, you will find essentially a set S. I'm giving you the set S. Check whether it is a one-to-one or not. Yeah.
So in the worst case, could the subset continue off?
Yes.
So
no, but yes, I agree with that order n. But I'm saying that what do you do? How do you check whether something is one-to-one? You want to write the code. So how do you write the code?
Check the degree.
Yeah.
Check the degree on the mapped set. So
good. How do you check the degree in order one?
So you first start with an array at the end.
Yeah.
And then for each element of this the set S, find f of S.
Yeah.
And then increment the subset corresponding index of the array.
Good. I mean, actually, here so here this is the idea. So you want to have an array for the second part. So if this is like we have mapping. So this is a subset. So this is a subset S prime of S. So here you want to have an array. So the degree, for example, array. And the degree of I here, you want to compute the degree of this guy, correct? For this part, for the right-hand side. Good. So for each element here, you will go and check what is the degree of that, and you will increase the degree of the guy. Actually, here instead of the degree, you can have a mapping instead of this as well. Instead of the degree, instead of an array, you can have a mapping actually. The same thing, because you will just see what is the mapping of this guy, and then you will increase that in the dictionary, for example. It's the same as array in this case. Good. So you will find a degree. This is order n. Why is it order n?
Because the subset S prime is at most n, and you need to run it on each element of the subset.
So that's exactly the thing that you need, because we want to go to the level that you can write the program. So you will go through this one. This is the for loop or while loop. You are doing it here, and then you are computing increasing the degree of that. So now we have the degree. It is order. Then what do we do?
Check the degrees. If it's either, if it's not one, then this mapping, this subset, it doesn't work.
Yeah, so it means that after the first for loop that you compute, so you will first compute degree. This is the first thing. This is like step one. In step two, what do you do? So first you compute it, that's order in that equation. Then what do we do?
Check the degrees, like loop through all the degrees.
Yes.
And then if any of them is not one, then that means this subset doesn't work.
And great. So if the degree is not, so then you will check degrees. What is the running time of this? At most order n, essentially, because it is at most S prime, and S prime is a subset of S, and we are assuming that the size of S is equal to. Good? Yeah.
Could the degree also be 0? I know it's still be 1 to 1.
Good. So that is the question. So we will check that one. So the degree, we want to check it. What would be exact if conditions that we should have it? So degree should be less than or equal to 1, or degree should be exactly 1, or what?
Exactly.
So the degree, this is important. The degree should be exactly 1. Why? Because that actually checks two things. If the degree of all these vertices in S prime, so these guys, if the degree of these guys are all equal to 1, if degrees are all equal to 1, we are done. It checks two things. The first thing is that, of course, the degree should be not greater than 1 because it's not 1 to 1. But if all of them are 1, it means that I mean, these are, say these are, I don't know, S prime. So say size of the S prime is, say, is equal to N prime. Good? So it means that if the size of this guy, so the size of this guy and these guys are equal, if the degree of these guys are equal to N prime, like if all of them are 1, it means that all these guys should come also to here. Because if one of these guys goes outside, then we are losing. Because we need exactly N prime, and it means that exactly all of these guys should come actually to this. So you did, this is a thing. So somebody say, okay, let's do this one and then check that whether each of them is like to the set S prime or not. So because if you don't check this one, so one option, of course, you should for the 1, you want to check that the degree of these guys are 1. The question is that after that, so we can say, okay, the degree should be equal to 1, you will check it. The question is that whether after that, do you need also to check that all this S prime, f of that belongs to S prime or not? No, this is not needed, because if all of them are equal to 1, it means that by definition, all of them should be mapped to the same set. None of them went out. So this extra step, you should not say that we want to do it because it's not needed. These are the things that they are checking you essentially on the interview. And of course, this is the efficient code. This is not just for interview. Does it make sense?
Yeah, I have a question. So, like, when I was looking through, like, say, like, you have check for the use rate something, how do you know that the other subset, has to be more than?
What do you mean the other subset has? No. That's exactly the thing that I mentioned. First, you need to compute the degree. At this point, you don't know whether the degree is 1 or not. First, you will go through the loop and compute the degree of this guy. The degree, how do you do that? Anytime you have this mapping to this guy, you will increase this degree. Then you have that one. Then when you're done, then you will go another for loop on this set S prime and check the degree of each vertex that you have computed is equal to 1. No, this is plus. So this is actually exactly the part that I have mentioned about 32 to the n versus 3n. You need to be very familiar. This actually takes time. I have seen actually very advanced people that they may make such a mistakes. So it's not a common thing. You need to do some exercise. That generally this kind of multiplications of the options. That when do we have 3n? When we have 3 to the n. So in this case, we are doing this operation and this operation. So this is additive. And this is not multiplication of these two things. Sometimes it is multiplications of these things. But here is, because, so essentially the idea is this one. When you write this one, you have this for loop that doing that. Then you have another for loop that you are doing that. I mean, this is the way that you will do it. Actually, this is the Pythonian version of writing it. That I like it because then in C++ you are using this. What do we call it? Not the brackets. What is the other? Square bracket. You are doing that, so you can do nasty things. And like my son is writing the code, said, don't do that because it's sometimes tempting. Like you don't need to have a next line or something. But actually, in Python, you can see if these have the same indent, means that that is addition. If one inside the other, then it means multiplication. So that's the Pythonian way of, seeing that if the indent are the same, it means that these are the things. But if one is inside the other, it means that it is multiplication. And here we have it not this case. We have it first, we are computing the degree, and then we are checking the degrees. So it would be order. So people at Zoom, any questions? Good. So you see, I want to go through the details of that. I don't want to give the solution. I want to essentially, this is like the style. So I don't want to give the fish. The fish would be that I will give the solution. That does not have that much use for you because probably they may not ask exactly this question. There might be some tricks, or sometimes if you are lucky, they may ask this question. But the one that is more important is that you will understand how you should do that. So, and how you should write the code. So here, if you want to do that, yes, for a given S, we can check it and then see what is the running time of it. That would be order N. Now, the question is that how many subsets do we have? Yeah, so how many subsets do we have? I know, I want others also to answer that. Actually, I want to say, like, I think the answer is 2 to them, but I want to say why 2 to them. That's better. Yeah.
Because each element could be in the set or not.
Okay. And how many elements? And then why is not 2 times n?
Because you do, each element has an option of being in or not, so it's 2 times 2 times 2.
Exactly. So that's very important. I want to be very familiar because that's like somehow the basic of the algorithm design. If you are not careful, something can be exponential. You can consider it like linear, and some linear can be exponential. And this is exactly the difference between backtracking algorithms and greedy algorithms. And also, in some sense, this is the main difference between P, polynomial time algorithm, and NP, NP complete problem that we will talk at the end of this class. So it is very important to distinguish between these cases. So we have 2 to the n. So what is the running time of this algorithm? So you can first try get all the subsets. Then there are 2 to the n options. And then for each of them, you need to have order n, correct? So the running time of this algorithm would be 2 to the n, n times 2 to the n, which is, it's better than 3 to the n that we had it before, but it still is not great. And one other question, how can you generate even all the subsets of sets? Let me ask others. If they didn't answer, I will ask you. I mean, that's great that you know that, but I want that others also think about it. Yeah?
Maybe some version of the request like divide and conquer that for each element you construct a subset that the element is in the subset and another subset with elements.
No, but I mean you are given a set n. This is a task. N is given to you. Only the input is n. Generate all the subsets of the sets 1 to n. Because that we need such a thing. For each of them, if you can generate all of them, for each of them, we can have a for on that things, and then run this algorithm that we discussed and check, and we will find the subset that has the maximum size. Anyone who can answer that? Yeah.
So maybe like they first start with subset, one element.
Yeah.
They go through 1, 2, 3, and then
How do you want to do it for 2, and then 3, then 4? How do you want to do that? Note that if you want to do it, if it is 3, then you need to have 3, 4 inside each other. Also, you want to make sure that the running time of all of them is equal to 2 to the n. That's also one other important thing. Yeah.
Create an n-bit string.
Create what?
An n-bit array.
Yeah.
And then use each bit represents whether this element is in the subset or not in the subset.
Yeah.
And then you can increment this array as if it is an integer and loop through all, increment it until all of them are ones.
Good. So, I mean, actually, we have mentioned the procedure before in some sense. Now, you know that how many subsets do you have? 2 to the n. So you can think about this one. Actually, in the procedure that we just discussed previous time, we mentioned how you can get a number and write a binary number of that number. Good. So you can actually do this one. Go from the number 0 to 2 to the n minus 1. For each of them, just compute the binary representation of this number. That's a simple way to do that. And again, when you have the binary number, I think as what was your name?
Chai.
Mentioned that each bit, if 0 or 1, it says that whether it is in the set or not. What is the running time of this algorithm?
Turn it into binary.
I mean, like the overall, yes. So you need to go through 1 to 2 to the n, say. Then what do you need to do?
Order n.
Then after that, you may need order n to change from that to binary. So it would be n times 2 to the n. You can do it actually more efficiently. As mentioned, you try to increment and say that so you may start with, as you mentioned, actually, you can start with 0, 0, 0, 0, and then you will add 1 by 1. You can say that actually, I think in this case, you can analyze it and probably it will be 2 to the n. You don't need to have this extra. But anyhow, if you pay 2 to the n, n is not that bad. Good. So you need to go through all. So whenever, this is actually interesting. This is a very easy implementation. You can do it actually with recursions. So that's also, you can do it with recursion. So if you want to write, this is the way that we talk about backtracking algorithm. You can say that for each element, you will decide 0 or 1, and then you will call this function again recursively until we will see the last element. That's a way also you can generate it. And that might be a bit, I mean, more tricky maybe to write. This would be an easier way to write. Just considering this binary representation, and then go through that, and each bit 0, 1, so that the set is there. So we can have, say, so the running time of this would be essentially n times 2 to the n, so n times 2 to the n times 2 to the n times n, another n that we need to check whether it is, so it would be n squared 2 to the n. Or maybe you can do it actually the other one. More efficiently, it would be n times 2 to the n. That is, I mean, this is one algorithm at least we can implement. We can write it down. And this is very important. I mean, this is like we are talking about different algorithms, greedy, dynamic programming, this one. At the end, it is important that the names, they don't work because you need to write a code that machine understands. So you don't need to say, I mean, that might be good, I mean, to talk, but you need to say, oh, maybe I can use the dynamic programming or this one. But you need to always be ready to give the details because this is, you're not talking to me at the end. This is, you're talking to this, I don't know. In some sense, maybe, actually, again, this is, I will say from my son, is this stupid computer is not understanding what I'm saying. Of course, I'm saying it's not for the computer problem. You don't mention it right to it such that it can run the code. So it's really not the problem with the computer, but in some sense it is stupid as well. That you have something, but you should mention it exactly the way that it understands. And if there is something wrong, means that you have written something wrong. Good. So that's the way that we have done it. And again, this was beyond this problem. I want to give you a general idea, how do we solve a problem? Good. And this is again the beauty of this. Like if you have, this is the way that I have done it before. So I had, for example, if I printed this page and then I have tried to written down this one, this would be a very nasty page and I cannot use it. But here I will just say this one becomes a very clean page. And maybe if I want to do continue some other reading here, I needed to have a new page. I maybe needed to have 2 copies. But here now you have the beauty of these things. Great. Okay, so we talk about this. So that's one way that, I mean, it is 2 to that. And the guy mentioned, okay, actually n is, I don't know, 10,000 or 100,000. What is it? So then you need to have a smarter algorithm. So you know that all of this we tried, it does not work well. So we came from this guy and we have discussed this one, that this was essentially the main issue, that this guy, if the degree of this essentially is greater than 1, then we have choices and this is the problem. But it means that the view that we have to the problem is not the correct view. We need to change our view. Good. Now, we want to change our view. So this approach does not work. We need to find another way. Otherwise, we cannot get anything for the solution. What should we do? Because you know I will ask you the last, if nobody knows. Anyone on the Zoom? Do you have any? Do you hear me well? Zoom? Please unmute and answer. Okay, so you will see everything well and you will hear me well. So this is the question now. Yes?
So why can't we just like, from the original final set that we have, just go through each and element and just like if the degree is 1 on both one, and so that's part of the subset.
Yeah. No, but I mean, here, for example, as I mentioned, so here, the degree of this guy is 1, correct? The degree of this guy is 1. The degree of this one is 1, so that is good. But the degree of this 1 is 2. But still, we can have this subset S prime, which is equal to 1 and 3. So the degree of this guy is 2 is not a problem in the general, because in the whole F, this degree is 2. But if we don't select 2, then the degree would be 1, and that should be fine. So, the people on Zoom, do you hear me well? Because I think you said that there is some internet connection. I just want to make sure that you are hearing me well.
Yeah, we can hear you.
Okay, good. So the issue that the degree 1 is in the whole mapping does not mean anything. Any other things that we can just, I will tell you the solution, then you will see, oh, that was very obvious, yeah.
Yeah, what was the question again?
So the question is that, I mean, here we had this algorithm, the running time was 2 to the n, say n times 2 to the n. But or n is n times 2 to the n. Good. But this is the problem. This is n times 2 to the n, correct? But n is, I don't know, n can be less than or equal to 10,000. So n can be very large. So this algorithm is not good. I want to solve still this problem. The person asked me, find the maximum set. So is the problem clear to everyone? Okay, so what can we do here?
So we can start with the entire set of A.
Yeah.
And then remove nodes, remove elements that are bad. So since we are removing elements, then eventually we can get to a point where everything on the right side has to be 1.
So what's the meaning of an element is so he said that, okay, start from the right-hand side and remove the elements which are bad. But here in some sense, 1 is bad as well. So what is the definition of bad?
It cannot, after something being removed, go to 1. So only things that cannot go to 1 are 0 now. So remove the elements that have degree 0 on the right.
Good. So essentially, that's the whole idea. Consider this guy 2. Let me just delete it. Consider this guy 2. I think that's the R point essentially. Then these 2 can be in or subset S prime on that. Why not? But I mean, what if we consider subset S prime? Does it help? So these 2, I mean, any subset that you will choose, no one will go to 2, correct? Because the degree of this guy is 0. If we checked it, essentially the algorithm that we check, we see that the degree of these guys, if a subset is given to us, the degree of these guys all should be equal to 1. Of course, the degree of this guy is 0. If we take any subset of these guys, maybe not the whole things, that does not help. The degree of this guy still would be 0. It means that this 2 guy cannot be in the set. Correct? We know that surely, I don't know about 1. 1 may or may not be there, but 2 cannot be there. Good. Now, if 2 cannot be there, what's the meaning of that? It means that if 2 from the, because it was essentially it was a 1-to-1 and this was a mapping from a set to itself. Good. So if 2 cannot be here, it means that 2 here also cannot be here, correct? It means that I should remove this edge as well. Good. And recurse, that's it. Anything, so you will continue. So this is important. 2, I mean, before for 1, I had this issue that I had a choice between whether I should choose 2 or 3 from that edge. But for here, when I consider 2 that has degree 0, I have no choice. These 2 guys should be gone from both sides. I just removed 2 from this side, then it means that the degree of this guy. So these 2 guys that it was there here, now it should be gone. So this edge should be gone. It means that the degree of 1 now becomes 1. Good. So in some sense, I remove the option of 2 by not going through the one that has the degree higher than 1, but to the degree 0. Those are the guys that I need to start with. So I will remove that. So then it is the case. Now I will come here. So if the degree of every guy is 1, if it is 1, I'm done because that's the best thing. I just removed the elements that I was forced to remove and I didn't remove anything else. So that's the maximum by definition. Good. Now, here I will say that whether the degree of each guy is 1, I mean, after removing 2, so 2 is removed. Then I will come to 7, correct? 7 has the degree 0, so it should be gone. Now 7 is gone. The degree of 6 becomes what? So it might be the case that the degree of this guy currently is greater than 1, maybe 10. But when you remove the other guy, the degree actually goes down. So in that case, the degree of 6 was 1 actually. I couldn't remove it at the beginning. But now I can remove it. Because the degree becomes 0, so I can remove 6. Good. Now, when 6 essentially removes, then it means that this edge also will get removed. Yeah?
So how do you know, like, actually, if we do a stability until like there's no thing with 0, at least that will be 1, 4.
I mean, That's by definition. Because you see the degree of these guys, you can think about it. You have n guys that are coming. If there is no guy here, it is 0. So if the only case that there is no zeros is that it should be 1-to-1. Because if one guy is 0, in some sense, this guy, I mean, you can consider n tokens that are given to you. If this guy has 0 token, it means that some other guys should have more than 1. So that's the idea. So if we know that the degrees are equal to 1, we know that if the tokens, there are n tokens that are given to you, this function. Now, these n tokens are coming, and the fact that this guy, none of them if one of them has 0, it means that one guy should have 2. But if everyone has 1, then everyone is 1. Then we are. So these are if and only. In some sense, this is the pigeonhole principle. Good. So we are removing 4 here, and then 4 is gone. Now the degree of 4 becomes 0 here. So I will come and delete 4 as well. After that, actually, I am done. So 1 has degree 1. So 1 has degree 1, 3 has degree 1, and 5 has the degree 1. And that's a solution. So this is also, I'm taking the similar items here. And you can see this is a 1-to-1 map. And this is the maximum that you can get.
So is it like by definition of mapping that like the left subset can no element can have more than one?
Yes, that is by definition. This is the mapping. This is the definition of mapping. Like the mapping also you have, for example, in C++ or dictionary that you have it. Each one has a key. So the key is that, like, if it is, you say f of 1, this is the index of array. That should be only one element you can go there. You cannot have 2 elements. That is by definition from that. So from this, essentially the question is that, like, by definition, the degree from each side, it is 1. From the left-hand side is 1. Because that's the definition of mapping. Good? Yeah, you have a question?
Could we have done this problem using cycles, like cycle detection?
Why do we want to do cycle detection?
So if there is a cycle, then the cycle must be 1-to-1.
Yes.
And if we found all the cycles in there, then it would also remove all the subsets.
Yes, but the issue that, so he's talking about, can we do the cycle detection? I mean, we are talking more about the graph. But the issue that essentially still you have this problem. For the one guy, you might have, I mean, sometimes you need to be careful whether these choices to create a cycle exist or not. Because you want to create a cycle, but you may have 2 outgoing edges. You want to, I mean, you need to be careful. Yes, I mean, you can say, oh, the mapping, you might be able to do that. So it might be possible, but you need to be careful. But in some sense, it should be the same algorithm. That cannot be that much different. What is the running time of this algorithm? Yeah.
Just O of n.
Is it O of n?
Isn't it O of n minus 1?
Just, I mean, that's exactly the problem. Try to write the code in your head. I mean, so we discussed at the beginning. So that is the same thing. First, we can compute the degrees. So you will compute degrees. What was the running time for that? Degree of this would be order. Then what do we do? Yeah.
So like if we want to know like the way we do it, you have to do it iteratively, so you have to go again. So like in this case, if either that for the first time, if there was nothing removed,
Yeah.
then you're done.
Yeah. So you see, first you need to find the degree 0. So that is order on. So you can say that essentially while there is degree 0, you need to do what? You need to remove it from both sides, correct? So, by the way, you can read it, this blue on the background, correct? It's clear. Okay, so this is the thing. So while there is a vertex of degree 0, you need to remove it. So we need to find the degree of vertex of degree 0. For that, what can we do? One easy way is that you will just go to all vertices. And then check it whether the degree. So this is order n, you need to go there. And then if there is a degree 0, you need to remove it. So how do you remove it? You will remove from this guy, and then you may make some bit that this guy, it will be not in my set. You will make that one false, something like this. Some bit that you say that this will be not in my finals. And then you will also decrease. So this is the case that I mentioned. So for example, if it is the case, if you know this guy is like this, so this is 1, 2, and this is 1, 2. You will remove this guy. You will find this degree of it. You will just say that you have a bit for this guy. Say you make it false. This guy cannot be the solution. And also you need to decrease the degree of 1. Good. That you can do it order 1. You will do it. So each loop contains these things. So you have a loop to go through all vertices and see which degree is 0. That is order n. How many times we need to do this loop?
So big O n squared for both of them, like to find that they could be 0, and then we do that n times.
Yes. So note that in each time, this is also important. Each time that this loop is going, one element will be if you are done, then done. If the degree of each guy is like essentially greater than 0, it means that all of them actually should be 1, and then you are done. So you will end the procedure and you are giving just out. However, if the degree is equal to, so if one vertex is degree 0, you will remove it. But how many elements can we remove total? What? N minus 1 essentially. Correct? At most n minus 1 element will be, so it is order n. So n times n to find this guy, and you are doing this n times would be what? N squared. So the running time, that we have it currently is n squared. Yeah.
You go to one for any time into the degree of 0, 1 million, then check the degree of the one that you determined.
Yeah.
See if that's 0.
Yeah, it might be, but it might be not 0. There is no guarantee that always that that you may, yes, it might become 0, but it may be greater than 1. If that greater than 1, that does not help you. You need to find another vertex of degree 0.
Yes, and so in that case, would you still have to go back after you've gone through all of the, you still have to go back and set it up?
Yes, the issue is that you need to for the people who are long, so I try to do it a bit more efficiently so that when we remove this guy, yes, if the degree of this guy is 0, then we don't need to go through the loop. We can just delete this guy. But the issue is that if the degree of this guy is not 0, you may need to go and find another guy. Maybe you want to say it is a continuation of the previous loop, but you need to be careful. So it needs a more careful analysis. And it's not clear that always, you can just do these guys and make sure that, so you need to think about it. Or we need to think about it for that way. But it's not that clear that you can do that one and make sure that the total is ordered. However, there is another way that actually you can make it order n log n. Yeah.
So you keep track of all the elements that you need to remove in a queue, and then while the queue is not empty, you remove it and check if you need to place new elements in the queue.
Exactly. So the idea actually, it is the priority queue. So this is the idea of priority queue. So the priority queue, actually, if you go there to the STL that I mentioned for C++, they have a data structure called priority queue. This is heap structure that we will talk later. But in short, this is the case. So we can have a priority queue. And so priority queue, you can say that who will be the first element of the queue. You can say that the first element of the queue would be the one that has the lowest degree. So what do you do at each time? You will essentially just find that element. If there is a 0 element, you will remove that. And then you need to update. So then you will reduce the degree of the other guys. And you need to make sure that this guy also comes up in the priority queue. So you need to do the update. This is one of the operations that you can do it in the priority queue. And this you can actually, this step at any time that you will delete one, you will find, so finding essentially finding the element with the minimum degree is order 1, because that priority queue is giving it. But then when you delete this guy, you need to change the order of this guy, because the degree of this other guy changes in the queue, that you may need log n steps. So it would be log n per each deletion. So then you have n log n if you are using period.
But if you use a normal queue, that would be linear.
If you use...
No, it would be constant.
If you want to do... yeah, but I mean, then the issue that you need to change the degrees of these guys. How do you want to change the degrees of the vertices in the queue?
What do you mean change these?
So you see, when you delete this vertex, for example, from 2, when you delete 2, then you need to remove this edge. The degree of this guy will go down by 1, correct? You need to have a data structure that always can tell you who is the guy that has the minimum degree and can keep this structure.
Well, then you don't need a structure with the minimum degree if you keep track of all the degrees.
Yes, but I mean, this is the issue. How do we want to keep track of all the degrees? That you need to be careful that the degrees, I mean, you are not doing any order n things.
So if you keep track of an array of all the degrees, you can easily update the degree and look up the degree in constant time.
Yes, you can do that, yes. But then you want to find the elements of minimum degree, correct? Degree 0.
That would be stored in the queue. The queue stores things with degree 0.
Okay, so good. So you want to have so this is the solution that you are saying. So you have a degree, these guys. So this is the case. So you have the degree element, the degree array, or the degree mapping. Then you want to have another queue here. So this is the queue of degree 0 elements, correct? So you have a queue of degree 0, correct? So you will go through this, you will read this one, you will add any guy whose degree is 0 first, you will add to this. Now, as he mentioned, so now you will find one of the first, where like one person from the top of this queue. You will delete it from the queue. You will come and you will see the degree of the guy that here is there. You will decrease it by 1. Good. So you will decrease the degree of this guy by 1. And when you decrease the degree of this guy by 1, what happens?
Zero.
If it is 0, you will add it to the end of this queue. Good. And you iterate. So then you can actually see that in each time, you are just removing one guy from here. We are doing order 1. And we need to do this one at most order n. So the running time of this would be order n. And you need actually order n, because generally getting below order n is almost impossible, because you need to at least read the whole 6. So this was actually an interesting example that we talk about. Like, we talk about 3 to the n, then we had it n to the 2 times 2 to the n. Then maybe we had n times 2 to the n. Then we talk about n square. Then we talk about n log n using periodic queue, and finally order n, which is out. And these are the type of things, actually, if you go to, for example, Geek4Geeks, that's a very good website for this. You will see exactly that this step is it. If you want to do trivial things like this, and then if you want to do it like this, then it becomes, you can do it better. Sometimes if you want to do the final one, in this case, actually, it was not very complicated. You just use the queue, again, the queue and the degrees, both of them are essentially what is in STL in C++, and you can do it. And I think Python also has queue. I'm not so sure Python has priority queue. I'm sure some module of that you can install and have it, but I don't think that it by default has a priority queue. Maybe I'm wrong, but that's anyhow. But here you will see that this data structure is one not complicated. It might be the case that to get this order n, it's actually you need more data structures, more complicated algorithms. So in that case, even like, for example, for interviews or others, generally it would be the case that the people, they said, okay, you need to say, okay, there might be better things, but should I implement? They said, okay, just implement the first algorithm, reasonable algorithm. Probably you don't want to implement this algorithm. That's very complicated. But you may say that, okay, I'm doing this algorithm, but say, can we do better? You may discuss and say, okay, this is another algorithm that you can do it. If you come up with this final algorithm at the beginning, that would be the best, of course. They will be very happy, and you will be very happy. If not, you may get the job at good. Yes. Yeah. Yes, I think, actually, so here when we have a dictionary with the key from this side. This is a different dictionary. Yes, I mean, you need to have the dictionary. I mean, you need to see who is the degree 0, and you need to decrease the degree. So the degree is very important.
Yeah, but you have a separate degree of it, or
I mean, you can have actually a mapping that from this side, I mean, that says that, I mean, it's an array essentially. You need one way or the other. You may need a mapping, or you may need an array that for each vertex, say what is the current degree of that, in degree of that. The in degree is the one that comes to a vertex. You need to have it. Great. So I think we have this one problem, but I think we went through the different things. And again, you can see lots of this example in Geek4Geeks. I actually strongly suggest you that you will go and see for different problems. And that's actually, you can increase the quality of your programming and thinking about it. And that will be very useful for this course. Any questions? Any question from the people at Zoom? Good. So if there is no further question, actually, we can finish. And yeah, just, do the assignments. Let me finish this.